Okay.
Very
First
good.
of all, thank you very much for the kind invitation to present my work here. It's a pleasure to participate in this conference. And I would like to talk about fractal structures in open, non-integrable Hamiltonian systems with some applications in plasma physics. My name is Ricardo Viana. I am from Federal University of Parana in the city of Curitiba in Brazil. I will divide my talk into those points. I would like first to introduce the theoretical model I am using to describe a problem in plasma physics. And since the Hamiltonian system I will talk about is open, I will talk about the concept of escape basins. And since these basins are typically fractal, I will talk about three ways to characterize this fractality: the fractal dimension, the basin entropy, and finally, I will discuss briefly the so-called Wada property and finish with my conclusions. I would like to thank my collaborators and students, Mrs. Amanda Matias, who is my postdoc in Curitiba, and my two PhD students, Leonardo de Souza and Pedro Herter. In fact, fractals are very important objects, both in mathematics and in applied sciences. Fractals, as you know, are self-similar geometric objects. They do not obey Euclidean geometry, and they have been studied for more than a century. Many important names in mathematics have studied fractals, like Julia, Fatou, Mandelbrot, and so on. It turns out that fractals occur very often in nonlinear dynamics, both in dissipative and conservative dynamical systems. And one of the most well-known structures, fractal structures in nonlinear dynamics, is the homoclinic tangle, which is the skeleton of chaotic dynamics, as has been proved first by Poincaré in the 1890s. We now know that the dynamics underlying the homoclinic tangle is based on a non-attracting chaotic invariant set introduced by Stephen Smale and called horseshoe. The horseshoe has a fractal structure, and this is reflected in the geometry of chaotic attractors for dissipative systems. And in open Hamiltonian systems, this Smale horseshoe is also present in a variety of structures. One of them is the so-called escape basins. One of the subjects in which this issue of escape basins could be important is plasma physics. We have been working for many years with theoretical models for the behavior of charged particles in fusion plasmas. And we have a number of experimental signatures of fractal behavior related to the these charged particles in both electric and magnetic fields. So these experimental evidences motivate us to investigate the presence of those fractal structures in theoretical models for the motion of charged particles in combined electric and magnetic fields. We are dealing with a quite simplified model for the behavior of charged particles in plasmas. In this model, we consider two kinds of fields: an electric field, okay, which is partly time independent, and electrostatic perturbation which depends on time. And we also consider the magnetic field, which is intended to confine the plasma. So in order to describe the drift motion of the particle, we are dealing with these guiding center equations of motion. Here I am writing this equation of motion in vectorial form, but we can open this equation into components in a local coordinate system. Unfortunately, I will not enter into many details about the geometry, but this coordinate system is able to describe the plasma inside a tokamak, which is a confining plasma machine, okay? So we have this differential equation for the components of the particle position, and we will deal especially with an electrostatic field, which depends on time. It's interesting because it's electrostatic. At the same time, we are dealing with a kind of electrostatic wave. And these electrostatic waves exhibit a broad spectrum of frequencies. And we will retain only one Fourier mode of this broad spectrum. And since we can express this infinite train of waves by a periodic sequence of delta function, it is possible to make a simplified description using discrete maps. So the path to obtain this map is very simple. We firstly define action angle variables, and then we rewrite the equations of motions in the Hamilton form. So we have here Hamilton's equations, which are obtained from a drift Hamiltonian describing the motion of charged particles in this combination of electric and magnetic fields. And since we use this kind of periodic delta function, we can sort of integrate these equations and obtain an two-dimensional Poincare map, which is area preserving. It is possible to demonstrate this both mathematically and physically. This comes from the non-dissipative nature of the motion. And in order to assign physical parameters to the various quantities appearing in those equations, we take parameters from a tokamak which is operating in São Paulo, Brazil. And I would like to show you some phase portraits of this map for typical values of the tokamak operation. And we can see a very familiar picture because we have a divided phase space. We can see over here quasi-periodic tori, we can see periodic islands, and we can see a quite large chaotic region. We are especially interested in this chaotic region because it is basically the exterior region of the tokamak. And this exterior region is particularly important because experimentalists are always interested in describing the transport of particles in this region. And once the dynamics over there is chaotic, we can use, at least from a theoretical point of view, a number of models and theories to describe this transport. And the concept of escape basing is very similar to the concept of the basing of attraction. The difference here is that we open the system by considering exits, and these exits are placed in the tokamak walls. So we are interested to know to what exit a given particle will hit after it collides with the tokamak wall. And so the boundary line, which is located over here is for a constant value of the action variable, we divided this boundary line into two halves, the left and the right one. And we consider the initial conditions leading to trajectories escaping the tokamak or escaping the plasma through either of these regions. So we can obtain the corresponding escape basins. And in this picture, we are plotting these escape basins using two colors, green and red. And we can see by a simple zooming of this region, the presence of fractal structures. And this is not by chance. This is exactly what we expect from the underlying chaotic dynamics of this region. So our goal is to describe this fractality. And the main reason for it is the presence of a complicated tangle of crossing invariant manifolds. And one thing that we have observed in all simulations is that the stable manifold of some periodic orbit embedded in the chaotic region, this stable manifold coincides with the boundary of the escape basin. This is not by chance. This is actually a consequence of the underlying dynamics. If we have one segment of the boundary over here, and we evolve this segment backwards in time here measured in number of map iteration, we will have that the accumulation of these bands is exactly the stable manifold. So we expect this fractal structure as long as we have a homoclinic tangle. But how we can quantify this fractality? There are many measures, there are many quantifiers that we can use in order to explain or to characterize this fractality. One of them, probably the most well-known, is the so-called uncertainty exponent, which is a concept very widely used in basins of attraction. And basically, the idea here is that we consider each initial condition in phase space with a given uncertainty epsilon. So we can talk about an epsilon vicinity of each initial condition. If this vicinity, which is a disk or a square, doesn't intercept the basin boundary, this initial condition is certain. But otherwise, if this disk of uncertainty crosses the boundary, we don't know a priori to which exit will a given trajectory escape through. So this disk is called epsilon uncertain. The fraction of those uncertain boxes or disks scales with a fractal basin boundary as a power law. And the exponent of this power law is called uncertainty exponent. A fractal basin boundary is characterized by a value of this exponent between 0 and 1. And it can be proved that this uncertainty exponent is 2, which is the dimension of the underlying phase space, minus the dimension of the escape basin boundary. So we can numerically estimate this uncertainty exponent in order to have an estimate for the escape basin boundary. We have done so for many values of the strength of the perturbation, and in all considered cases, the results are very consistent because we have very small values for this uncertainty exponent, and these very small values are related to a fractal dimension nearly equal to 2. So the escape basin boundary turns out to be almost an area filling curve. This is a very problematic, this is a very troublesome situation from the point of view of the final state uncertainty, because if this exponent is nearly zero, we don't have any chance of improving the knowledge of the final state, even if we perform a drastic reduction of the uncertainty. You will not decrease in a significant way the uncertain fraction. And this is a very complicated situation. It prevents us from saying to what exit will the trajectory go. But this is not the only way to make this characterization. Very recently, Álvaro Daza and his collaborators, among them Miguel San Juan, they have developed a new concept called basin entropy, which is essentially based on an application of the Gibbs entropy to the case of fractal basins. Fractal basins of attraction or fractal basins of escape, like in the present work. And the idea is very simple. We cover the phase space region occupied by a chaotic orbit with a fine mesh. And we consider for each box of this mesh the probability to go to one or to the another exit. These probabilities are used to compute the Gibbs entropy in the same way as the thermodynamical entropy. And this entropy is computed for each box. If we sum over all boxes, we have an entropy of the whole grid. And since this entropy is extensive, we can obtain a relative measure by dividing by the size of the mesh. So this basin entropy is a quantifier of the complexity of the basin boundary. Just to give you two limiting cases, if I have a single exit, I will not have any uncertainty because every trajectory will escape through the same exit. Accordingly, the relative probability is unity, and so the entropy is zero. By contrast, if we have completely equiprobable exits, okay, it is easy to prove that this entropy will approach the log of the number of exits. In the case of two exits, it approaches log of 2. The same idea can be applied to the basin boundary entropy. The difference is that we divide the extensive entropy by the number of boxes which contain points of the two basins. Or in other words, we divide by the number of boxes covering points of the basin boundary. And it is possible to characterize the fractality of the basin boundary using this measure as well. So we have done these calculations for our system, and let me show you our results. Here we can follow three quantities. The black squares stand for the basin entropy, and we are showing here the variation of this basin entropy with the strength of the perturbation. And as you can see, the fractal dimension is nearly equal for all the cases. The fractal dimension here is not good for describing final state uncertainty, but the basin entropy is excellent to do so, because you can see that the basin entropy goes from 0.1 to almost the theoretical limit of log of 2. So in this case, the basin entropy is a superior quantity to characterize this fractality. In blue circles, you can follow the variation of the basin boundary entropy, and it follows the same trend. And just to compare, in red squares, we compute the relative area of one of the basins. In these three measures are consistent in the sense that they present a clear trend towards higher values. Let me finish my talk. I think I have some minutes more. I would like to present you a very interesting phenomenon which occurs in a quite general way in many dynamical systems. And basically, it is illustrated by the problem of the basins of Wada. Basins of Wada are a geometrical construction, and we basically have three lakes, and the boundary between these three lakes is a boundary point in which vicinity you have points belonging to all basins. This seems counterintuitive, and it is, at least for smooth boundaries, but not for fractal boundaries. A very interesting illustration of this phenomenon occurs here in Brazil, where you have near the Iguaçu Falls, one of the touristic landmarks in Brazil, you have a three-frontier mark, which is the point where the frontiers between or among Brazil, Argentina, and Paraguay meet together. Once these boundaries are smooth curves, these Wada points are expected to be exceptional. But for fractal boundaries, it turns out that nearly all points can be Wada, or at least a fraction of them. And in the case you have this Wada property, the question of final state sensitivity is even more complicated because you have a very intertwined structure of basins in all scales. And we have investigated the presence of this property in our problem. But in order to do so, we have to carve three exits instead of two. And we divided the tokamak wall into three equal thirds and considered red, blue, and green points belonging to the corresponding escape basins. And you can see, even a very superficial inspection of the figure, that the patches or regions belonging to the three basins are densely intertwined. Obviously, this is not a characterization of the quantitative characterization of the Wada property. So in order to do this task, we have used another quantitative measurement of this Wada property called the grid approach. It was developed by the same group in Madrid. And basically, this grid approach consists on an iterative way to classify points in the phase space. Basically, we classify those points into three categories. One category contains points belonging to the interior of some basins. We call them interior points. They are not in the boundary. If the points belongs to a boundary between two basins, you define this set as J2. And if the point belongs to a boundary between three or more basins, we define a set G3. And this method proceeds by successive approximations. In each step of this iterative process, we compute the relative number of these points, and this relative number is called W. And basically, if W2 is 0, you don't have Wada property. Otherwise, if it is equal to unity, you have a full Wada property. And from 0 to 1, you have a partial Wada property. I will show you here our numerical results. After some steps of refinement, we have observed that approximately 96% of the points are from the set G3. So the escape basin boundary is almost completely Wada. So I will briefly put my conclusions. We have considered a problem involving the behavior of charged particles in combined electric and magnetic fields. We have a theoretical model predicting chaotic behavior in the region near the tokamak wall. And this chaotic behavior in an open system will lead us to the concept of escape basins. Due to the chaotic nature of the orbit, this escape basin is expected to be fractal, and we have been able to characterize this fractality using the uncertainty exponent, the basin entropy, and finally the Wada property. So thank you very much for your kind attention, and these are recent papers dealing with this subject. Thank you very much.
Okay, thank you very much for your presentation. Now we have time for questions, please. I see a hand. Maybe I should start with a simple one from my side. So these maps which you discussed at the first part, talking about these charged particle flows, you reduce these the original complex problem to a low-dimensional Hamiltonian system or driven system. Now, if you go back to the, I mean, how robust is that? If you consider going back to the original many-body system, if you wish, so because then tori don't hinder any more chaotic trajectories from escaping, and so on and so forth. How is this entire escaping theory robust with respect to increasing the number of degrees of freedom?
Perfect. Thank you very much for the question, Sergey. This is a very important problem. One thing that I didn't say when I described the system is that the charged particles I am describing in this model are not proper plasma particles. They are intended to be impurity particles. These impurity particles come from many sources. One of them is the contamination of the plasma. And since these impurity particles do not interact significantly with the plasma, we can consider them a passive particles, like in Hamiltonian problems of passive advection. So these particles are being actually advected by the E cross B field in the plasma. So this model is robust in the sense that we can treat these particles as individuals without interactions, because the density of the impurities is intended to be, or needs to be, low enough to this approximation to be valid. So it's really an important point. Thank you for raising it.
Okay, thank you. Maybe now we have questions from the audience. Okay, I have a follow-up then from my side. That's more maybe a technical one. So when you computed these, how did you call them? The escape basins. Then my question is, how is the round-off error on your CPU impacting that? If you take another CPU, another maybe compiler or whatever you use, how robust are these results? Because round-off errors propagate in chaotic dynamics, and then maybe things go rogue after a few iterations.
Yes. Actually, these round-off errors can be partially responsible for the uncertainty. So if we consider numerically generated trajectories, we are always dealing with uncertainties, even if we don't, if we have a theoretical model, these uncertainties are still present. So this characterization is important because, in principle, if we have individual trajectories, these individual trajectories may be giving us the wrong information. So physically meaningful results are expected after a bunch of trajectories, an ensemble of trajectories, in the same way as other quantities like Lyapunov exponents are computed. So this problem is in the heart of the interpretation. Yes.
Thank you. Last call for questions. Well, it doesn't seem to be the case. So let's then thank Professor Viana once again. Thank you very much.
Thank you very much, Sergey. And
then I think you can, yes, probably.
Okay, I have to stop sharing my...
Unshare, yes.
Unshare. Just a moment, please. I will